In this mini-lesson, we will go through an example involving a rigid object in static equilibrium. We begin, however, with a brief review of the underlying principles. We've seen static equilibrium before for situations involving translational motion only. We said that an object was in static equilibrium if it was stationary and if there was no net force acting on it. That means it is not accelerating and thus remains stationary. We ignored the possibility that the object might be able to rotate, and in that sense we treated the object as point-like. However, real objects aren't point-like, they're extended, and that means they can rotate as well as translate. Therefore, we need to augment our definition of static equilibrium accordingly. We say that a rigid object is in static equilibrium if it is stationary both translationally and rotationally, if there is no net force acting on it, and if there is no net torque acting on it. This means that the object has neither translational nor rotational acceleration, and so remains stationary both translationally and rotationally. The main conditions for static equilibrium are expressed mathematically in these two equations. Any forces acting on the object must add up to zero, and any torques acting on it also add up to zero. Note that these are vector equations, and therefore must hold component by component. At this point, it would be reasonable to ask, about what point is the net torque zero? After all, torques are always calculated with respect to a specific point. However, for statics problems, it turns out that the net torque will be zero about any point. We are free to choose any convenient reference point for computing torques, as long as we are consistent in that choice throughout the problem. We'll see how this works shortly, but now let's do an example. A fisherman is posing for a photo with his prized catch. The 6.0 kilogram fish hangs from one end of a rigid 1.0 kilogram pole, with the other end resting against the ground. The pole makes a 70-degree angle with the ground. The fisherman holds the rod at its center and exerts a horizontal force. Everything is stationary. Find the force F exerted by the fisherman and the horizontal and vertical components of the force exerted by the ground, G sub x and G sub y. As always, we start by drawing a good picture. Next, we indicate all forces acting on the pole, making sure to place the vectors at the location they are applied. We're told that the fisherman exerts a horizontal force on the middle of the rod, and we can treat the weight of the rod as if it acts at the center of mass, which is also at the middle of the rod. The weight of the fish acts at the top of the rod, and the ground exerts a force on the bottom of the rod. Since we don't know a priori the direction or magnitude of the force the ground exerts, we represent it by separate components, G sub x and G sub y. I've chosen to make the y component point up and the x component point to the right. But if either of those choices turns out wrong, it will show up in the math by giving a negative number. For the sake of clarity, it is useful to get rid of all but the important parts of the drawing, like so. We're told that the pole makes a 70-degree angle with the ground, and this means the fisherman's horizontal pulling force makes an angle of 70 degrees with the rod. Similarly, the weight of the pole and the weight of the fish both make 20-degree angles with the pole, because 20 degrees is 90 degrees minus 70 degrees. There are four unknown quantities in this problem: the fisherman's pulling force F, the x and y components of the force exerted by the ground, G sub x and G sub y, and the length of the rod, L. However, we only have three equilibrium equations in this problem. The x and y components of the net force are both zero, and the net torque is zero. This seems at first to be a problem because we have four unknowns and only three equations. But as we'll see shortly, the length L drops out. Let's start with the two force equations. The only horizontal forces are F and G sub x. Static equilibrium tells us that G sub x minus F equals 0, so G sub x and F have to be equal to each other. For the vertical forces, we get G sub y minus little m times g minus big M times g equals 0. Or G sub y equals the quantity little m plus big M times g. We could plug in numbers at this point, but let's save that for the end. For the torque equation, we first have to choose a point to calculate torques about. We can choose any point we like, but it usually is best to choose the point where the most forces are acting. In this case, that's either the bottom of the pole, where G sub x and G sub y act, or the middle of the pole, where F and little m times g act. Why are these desirable choices for reference point? Because forces that act at a point don't contribute to the torque about that point. So the torque equilibrium equation is simpler, i.e. has fewer terms, if we choose one of these 2 points as the reference point. We'll do it both ways just to show you get the same answer. Let's first start with the bottom of the rod as the reference point for torques. The pulling force F would tend to make the rod rotate counterclockwise about the bottom point, while the two weight forces would tend to make the rod rotate clockwise. Therefore, F gives rise to a positive torque, and the other two, negative torques. Obviously, neither G sub x nor G sub y would tend to make the rod rotate about its bottom end, and thus contribute nothing to the torque about this point. Both F and m sub g act at a distance L over 2 from the reference point, while big mg acts at a distance L from the reference point. Therefore, given the angles already discussed, the net torque on the rod about its bottom point is given by L over 2 times F times sine of 70 degrees minus L over 2 times mg times sine of 20 degrees minus L times big mg times sine of 20 degrees equals 0. Solving this for F gives F equals the quantity 2 times big M plus little m, that quantity times g, times sine 20 degrees, all over sine of 70 degrees. And plugging in values for big M, little m, and g, and evaluating, gives the pulling force F equal to 46.4 newtons. Since G sub x equals F, G sub x equals 46.4 newtons as well. And finally, evaluating G sub y gives 68.5 newtons. Now let's repeat the calculation, but this time calculating torques about the middle of the rod. For this choice, F and little mg produce no torque, but G sub x and G sub y do. So we no longer care what angle F and little mg make with the rod, but we do care that G sub x and G sub y make angles of 70 degrees and 20 degrees respectively. Nothing changes in the force equations, of course, but the torque equation now takes on a different form. G sub x would tend to make the rod rotate counterclockwise about its middle, whereas G sub y and big mg would tend to make it rotate clockwise. Thus, G sub x gives rise to a positive torque, and G sub y and big mg negative torques. All three forces act at the same distance, L over 2, from the midpoint. So the net torque about this point is L over 2 times g sub x times sine of 70 degrees minus L over 2 times g sub y times sine of 20 degrees minus L over 2 times big mg times sine of 20 degrees, all equals 0. Solving for g sub x gives g sub x equals the quantity g sub y plus big mg, that quantity times sine of 20 degrees, divided by sine of 70 degrees. But g sub y, we already know, is equal to the quantity big M plus little m times g, which we can substitute in to obtain g sub x equals the quantity 2 big M plus little m, that quantity times g sine 20 degrees, all over sine of 70 degrees. And plugging in numbers, we obtain 46.4 newtons. And therefore, F is also equal to 46.4 newtons, and g sub y equals 68.5 newtons. As you see, we get the same answers that we got using the bottom of the rod as the reference point for torques. For practice, you should try doing this problem again, but using the top of the rod as the reference point for torques. You should get the same answers. For statics problems, it just doesn't matter which reference point you choose, so choose whichever point is most convenient.